Hello friends, this video on chemical bonding part 21 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched part 1 to part 20. Let's draw the shape of methane, ammonia and water with whatever knowledge we have till now. So let's take this carbon molecule now. Carbon, we know that it has atomic number of 6. 1s2, 2s2, 2p2. Correct. So this will be my 1s orbital will have 2 electrons. 2s orbital will have 2 electrons, and 2p orbitals will have 2 electrons. So let me put one each here. One this p orbital, one p orbital. Correct. Now I am saying that in the excited state it will be something like this. It will be 1s2, 2s1, 2p3, right? So I'll remove one electron from here and I'll put somewhere here. Excited state, one electron jumped and came here. This is my excited state of carbon. Now I'm adding 3 CH4. So I have to add 4 hydrogen molecules. So what I can do is I can add 1 hydrogen here, 1 hydrogen here, 1 here, and 1 in this, right? So this will be my sp overlap, this will be sp overlap, this will be sp overlap, and this will be ss overlap, right? Because both are s orbital. So this will be shape of my hydrogen molecule. That means these angle will be 90 degree. Correct? But experimentally we have seen that carbon shape is something like this, 109 degree. So we are doing something wrong, right? Because we knew the carbon shape is like this, then we added as hydrogen for hydrogen, it should be 90 degree because all these orbitals are 90 degree apart, but the shape is not like this. Similarly, let's draw for NH3. For NH3, we know that nitrogen is 7 atomic number. So 1s2, 2s2, 2p3. So let's put 2 electrons here, 2 electrons somewhere here, and 3 electrons in 3 orbitals. Right? I have to add 3 hydrogens. So let me add 3 hydrogens here. Because I told that the unpaired orbitals will overlap. So this is unpaired, this unpaired, this overlap. They should get ammonia and each angle should be 90 degree because these orbitals are 90 degree apart. But experimentally we saw that NH3 angles are 107 degree. Also if you see water also, water I have oxygen, oxygen is 1s2, 2s2, 2p4. So I have in 1s2, 2 molecules here, and 2p4, 1 I'll put in all 3, one more I'll put somewhere here only. So I have how many unpaired orbitals? 2 here. So my hydrogen, let's suppose, will come here, will join here, and hydrogen will join here. Because hydrogen is having unpaired electron, right? So it will pair according to the current theory we have, orbital overlap theory. So the angle should be 90 degree. Because these are 90 degree apart, orbitals, p orbitals, but the experimental value is 104 degree. So there is something they're missing because with the current knowledge we have for the orbital approach, orbital overlap, and the current knowledge we have for the structure of atoms, which we learned in the last class, right? Carbon will be something like this. It will have 4 unpaired orbitals in the excited state. So we added 1 hydrogen each in all these 4 orbitals, unpaired orbitals, we get something shaped like this, which should be all 90 degree, but the experimental value is different. In ammonia also, we have 3 unpaired orbitals, and we add 3 hydrogens to this 3 unpaired orbitals. It should be something like this, all 90 degree, right? It should be something like this, because all these orbitals, p orbitals, are 90 degree with each other, but experimental value is something else. case of water also, when we applied this current knowledge we have, we found that the angle should be 90 degree for hydrogen, and this it should be this value, but experimentally we found this value. That means something we are doing wrong, right? So the current overlap concept is not able to explain the structure of the molecules. So what should we do? Here comes hybridization. Hybridization, in order to explain the shapes of these molecules, Pauling introduced the concept of hybridization. Right? According to him, according to Pauling, the atomic orbitals recombine to form new set of equivalent orbitals. That means the oxygen here, or the carbon here, or the nitrogen here, these molecules, these atoms, their orbitals will recombine to form new set of orbitals, and they are called hybrid orbitals. That means the orbitals of central atom, generally this hybridization happens only for central atoms, recombine to form hybrid orbitals, and this is what hybridization says. Because the shape of all these molecules you could not explain without hybridization, so he introduced a new concept called hybridization. He is saying that the Pauling says that this is the central atoms, their orbitals recombine to form hybrid orbitals, right? And we should not use pure orbitals, we should use hybrid orbitals for bond formation. And with this, if we do that, we can explain the shape properly. And the formal definition of hybridization is nothing but process of intermixing of orbitals of slightly different energies. Please note, slightly different energies, so as to redistribute their energy, resulting in formation of new set of orbitals of equivalent energies. For example, if I have orbitals of energies 4, 3 and 5, right? So they'll merge. 4 plus 3 is 7 plus 5, 12. 12 by 3 is 4. So they'll form 3 orbitals with energy 4. That means if they are orbitals of slightly different energy, they'll recombine, they'll intermix, and they'll redistribute their energy, and they'll form new set of orbitals of equivalent energies. Please note here, it's a critical point here. If they are orbitals of slightly different energies, they'll recombine, they'll redistribute energy to form new set of orbitals for equivalent energies. And shape will also be same. The example is 2s, 1 2s and 3 2p. All are having equal energy, right? 2s, 3p are almost similar energy. They'll recombine to form sp3 hybrid orbitals. Correct? And it is not that carbon always form sp3. Carbon will form sometimes sp, sometimes sp2, sometimes sp3, depending on the condition. But the fact is, the orbitals of equivalent, almost similar energy can combine to form equivalent energy orbitals. Right? For example, I told the energy is 4, 3 and 5, 3 orbitals, they'll combine to form again 3 orbitals. I'll write once again, 4, 3 and 5. Orbitals may combine to form again 3 orbitals, or with same energy, 4, 4, 4, same energy and same shape. This is called hybridization. The features of hybridizations are, the first is the law of conservation of orbitals. That means the number of hybrid orbitals, the output is always equal to the number of input. The number of atomic orbitals, you can hybridize. Law of conservation of orbitals. For example, I told there are 4, 5 and 3 different energies, similar energy, similar not equal. They hybridize to form 3 different orbitals, all will have same energy. So if 3 orbitals are used here, you will get 3 orbitals. If 4 is used, you will get 4. That is law of conservation of orbitals. The hybridized orbitals have same shape and energy. As I told, they'll have same shape and energy. Energy is same and shape is also same. and the hybrid orbitals are more effective in stable bonds. See, the whole story is all about stability, right? Decreasing your energy, decreasing your stress. So it is saying that the hybrid orbitals are more effective in forming more stable bond, and that's why hybridization comes into picture. And as I told that, since these guys have same shape and structure, and if you see in the Vesper also we have, let's suppose 3 balloons, it will have 4 balloons, it will have this structure. You put 2 balloons, it will have this structure, linear structure, right? If you have 3 balloons, it will have triangle planar structure. So since all the balloons were same shape and energy, here also all these orbitals have same shape and energy, right? All these orbitals, as I told, have same shape and energy. So that's why they'll try to get a particular shape such that they have minimum repulsion, and that's how they indicate the geometry of molecule. So it's almost similar to Vesper theory actually. There also it talks about different balloons, right, of same shape and energy. So when you put 3 balloons of same shape and energy, it will be in this triangle planar form. Similarly, in this case also they're talking about hybrid orbitals of same shape and energy, right? And they try to be in the space in such a way that they give minimum repulsion between the electron pairs, and thus they have stable arrangement. So, and thus you can see the hybridization indicate that. Before we go further, let's understand the conditions for hybridization. The first condition is the orbitals present in the valence cells only take part in hybridization. The second condition is that the orbitals that are undergoing hybridization should have almost equal energy. For example, I told 4, 3, 2 by 2, I think. Yeah. See, they hybridize, they'll form 3 hybrid orbitals of same energy and same shape, but these are almost equal energy, right? The promotion of electron is not mandatory prior to hybridization, and it is not necessary that only half-filled orbitals take part in hybridization. In some case, even the full-filled orbitals also take part in hybridization. Carbon, oxygen and nitrogen tends to hybridize maximum. Carbon, nitrogen, oxygen, please remember these 3. They tend to hybridize maximum. Terminal atoms, such as hydrogen, chlorine, fluorine, they don't hybridize that much. But carbon, nitrogen and oxygen, they tend to hybridize a lot. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.